Hello, everybody. Can you guys hear me yet? Hello, everybody. Can you hear me? I barely see anything here. Could somebody write a note if you hear me or you don't? Here, can you hear me? Boy, things are moving very, very slow. Can you hear me? Let me see if anybody can hear me. Let's see. Can you guys hear me? I just wrote this note to the admins to see if they see me online. Let me see. Nobody's responding. Let's see. Oh, okay. So you can hear me. Okay. I don't see anybody noting anything. I cannot see any comments, but I got a confirmation from Christine that you guys can hear me. And I don't know if you can see me. So if you can see me, let me know. I don't see um, any of the comments. I don't see anybody. So let me see. Share to groups. Oh, maybe it hasn't been shared to the groups. Let me see. My computer is having trouble. I'm having some trouble. Let me see if I'm gonna restart it again. Hold. Actually, no. Let me see. Okay. So Christine can see me. Okay, very good. So I cannot see any of you, and I cannot see any of your comments. This is something that I guess Facebook is reinventing every single time. So I'm very sorry if I cannot see you and I cannot see any of your questions. This is kind of weird. Okay, so let me talk to you about the questions that you have asked of me. And there were a lot of questions. There were some that were left over from the previous discussion that I presented when I was not able to finish because I had a cough attack. So hopefully this time I'm not going to get a cough attack. I have a little bit of water with me so I can cancel that out if that happens. But so I wanted to start with the question that Truck asked. Truck asked to explain what CISO is. And CISO is CICO. And what it actually stands for is calories in, calories out. And so this is a very old trick where we believed, and it has been proven to be incorrect, that whatever calories we consume, we will expend the equal amount. And while in terms of physics and mathematics this is true, there are a lot of variations here. Because if you look, for example, when you die, what actually happens to you, you have all your spirit and all your life is gone from you, but you still, even millions of years from now, if you just die and the soil is just burying you, but they dig you up, then several thousand years from now, they're still going to find your bones. So you still haven't expended all your energies that you have consumed. There's energy left inside your bones. So how did that get there? Given that all the energy that you eat is supposed to be expended, but clearly it isn't expended, it's also saved. And some of it isn't saved because the bones have somehow they appeared, right? They were created from something to something. And that itself took energy. So when we talk about CISO, most people understand this as equivalent to you're eating 100 calories worth of something, and then you exercise 100 calories worth and you expend that much energy, then you just spend all the energy that you just ate. But it doesn't actually work that way. And there's obviously some clear understanding why it cannot work that way. One of the reasons why it can't work that way, obviously, is because even after you die, you have leftover in you. And so this is sort of kind of like death calories. How did that happen? How did those calories deposit into bones? What was required to deposit that into bones? And is it the same for all people under all circumstances and all kinds of foods? And so here we come to the kind of foods, because if what calories in is equivalent to calories out, then it automatically implies that it doesn't matter what calories you eat, they're all the same. So I have a couple of examples here that I went through the USDA database and searched out, and you can search it yourself and you may come up with different numbers because there are a lot of options there, but these are USDA standard choices. So if I want to eat 1,000 calories worth of something, so I chose to look at watermelon. In order to get 1,000 calories worth of watermelon, I have to eat approximately, I would say about a whole watermelon, because 100 gram watermelon is 30 kilocalories, so it's 30 calories. So that means you need to eat 787 grams. So that is a lot of watermelon, and that, you have to eat that much because if you recall, there we have glucose or carbs, and they provide us 4 calories or 4 kcal per gram. And then we have protein, which provides also 4, a little bit less apparently, but say 4 kcal per gram. We also have fat, which provides 9 kcal per gram. And then we also have alcohol, which provides 7. And so when we're looking at the different kind of foods, they provide us different energies. So we need to account for that. Now, watermelon has almost 0 fat and it has almost 0 protein. So it's pure sugar and water. So you have to eat, and it's a lot of water. And so you have to eat a lot of watermelon. Apparently, you have to eat 787 gram of watermelon, which is nearly 2 pounds, in order to get 1,000 calories out of that watermelon. Now, when you eat 1,000 calories in meat, you obviously is going to be a meat. It has a combination of fat and protein, and it also has a little bit of carbs because meat contains glycogen, although very tiny. And so the amount of meat that you have to eat to meet the 1,000 calories is much less. In ground beef, and this is 80% lean, I believe, you have to eat 400 grams. So you're talking about almost 800 gram in watermelon, but only 400 gram in meat, in ground beef, 14 ounces, because it's just so rich in fat and protein. And then I also looked up ribeye, that's my favorite one. This is a full ribeye with a cap on, and the fat is taken off, but it's a full ribeye, and you have to eat 534 gram, which is approximately a pound of ribeye that you have to eat. And so a pound is 16 ounces, so it's really practically 1.5 servings for a day for every one of us. Not that we eat a whole watermelon every single day. And then so also looked at ghee, which is just pure fat. Ghee is just the clarified butter, so all of the lactose part and all the animal part is taken off of it. It's just pure fat. And obviously this is the richest because fat provides you 9 kilocalories per gram. So to get 1,000 calories in ghee, you really only have to eat 114 gram, which is basically, if you're looking at just a stick, it's about like this, a little stick, or if you're getting it the brick kind butter, it's about half a brick. And then if you create clarified butter from that, so you can choose to eat that itty bitty piece of ghee, or you can choose to eat a whole watermelon, or you can have a pound of steak. So you can see there are huge differences. Of course, I didn't calculate it in alcohol, but alcohol is 7 calories per gram, and watermelon is 4. So in watermelon, I have to eat 1.75 pounds. So in alcohol, probably approximately about 1 pound of alcohol. And alcohol is a fuel. It can totally burn just like anything else. Of course, it creates a lot of byproducts. So let's talk about what these different types of foods create in us and how these foods convert into energy in us. So we can see that even though they're all 1,000 calories, they behave very differently in our bodies. So, watermelon. If you eat 1,000 calories in watermelon, forget about the fact that you just ate a lot of water and you're going to be peeing your head off and you're going to be very uncomfortable. Still, it's 1,000 calories. So, there's sugar in there, which gives you 1,000 calories. That amount of sugar, there's no way your body can use right away. So, here we immediately run into a problem is that if you eat more than what you can burn at that time when you're eating it, you have to store it somehow. So, how do you store glucose? That's very interesting because glucose is a toxin in the blood, so you can't store it in the blood. We have glucose in our blood because our red blood cells need glucose. Otherwise, if the red blood cells didn't, we may not have any glucose in our blood and we would be totally fine. So we really need it mostly for the red blood cells. There are some other little organ parts like our eyes that can't use anything other than glucose, but it's require minimal. In the brain, there are a couple of cells that require glucose, but they can also go by lactate, so it isn't necessarily glucose per se. And lactate is a byproduct that can also be created from protein. And then in the kidneys, there's one particular area where a little bit of glucose is needed. But so we basically think of glucose as an important fuel because it's in our blood, but it really isn't an important fuel. It's an important fuel in our blood for our blood. The blood can only use glucose. And so when we eat food that has glucose or carbohydrates in it, we basically fuel our blood and nothing else. And so when we're looking at it this way, what is going to happen to all that extra glucose that's coming out of the watermelon? And that glucose very quickly has to be stored, and it will be stored one of three ways. It can be stored as glycogen. The glycogen, in order to store it as glycogen, the glucose has to go up to the blood, to the liver, and in the liver it has to be converted into glycogen. Glycogen is like longer chain starch molecules. So starch, like potatoes, is an easier form of storing glucose than storing glucose itself. And so glycogen is like a long chain of starches that our liver and our muscles can store. But there's a limit to how much we can store. There's only enough room for about 130 calories worth of, or 130 grams worth of glucose in our liver, and about 300 or so grams worth of glucose in our muscles. And then after that, and we just ate more than this, we ate more than 400 gram glucose with the watermelon. So what is going to happen to the excess glucose? And of course, we were not empty of glucose to start with. So we had glucose in our blood, we had glucose in our liver, in glycogen, and we also had it already in our muscles as well. And so we had stored all of these already before we ate the watermelon. This is something that's ongoing. So what's going to happen to all that, given that we have all those fields? So we may need to add a little bit of extra glycogen to the liver or to the muscles, but definitely don't need to replace the whole thing. So what's going to happen to that glucose is that it won't be able to be stored as glycogen. And so then the next thing that is going to be stored as an option is either it's going to convert to lactate, which I mentioned earlier can be used by some of our organs as glucose, and then as lactate will go back to the body, see if it can then be used as glucose again. And if it can't, it'll go back into the liver one more time again, and then it's going to be converted into triglycerides and stored or used as free fatty acids. And so when we're talking about eating this much carbohydrates, though, we can't really use all those free fatty acids because we are burning mostly glucose. So everything will be stored as triglycerides. And so this is one of the reasons why you can see that people who eat a carbohydrate-rich diet have high triglycerides. They can't use them and they store them, and it's quite unhealthy as well. So as you can see, we have a problem here because we ate all this watermelon. We can't actually use the energy from the watermelon, so we have to store it. And the storing process itself is quite expensive. Storing glucose, having to go through all these processes of putting the glucose away in the form of glycogen or converting it to triglycerides this takes a lot of energy, and depending upon who you are, and depending upon what metabolic process you're in, whether you're in ketosis or not, this can be a very simple or very complex process. And it also depends on your metabolic status. Because if your metabolic status is unhealthy, then the chances of this glucose being used versus stored is going to be quite different from a person who has a different metabolic status. Also, age matters. If you're very young, this amount of glucose is going to be stored very easily and uses energy quicker because you simply are more energetic and everything is growing about you. It's not only that you're more full of energy in terms of try to run after a 1 year old as he or she starts running around, but also they're growing. And so their insulin is used as a growth hormone rather than as a growth hormone. Horizontally, it's a growth hormone for the whole body. So all the organs and height, everything is using insulin as part of growth hormone. And so if you're eating that watermelon, the energy production and the protection of that energy for future use is going to be very different from when I eat, for example, fat. And I want to bring fat first before I talk about protein. So if I eat that butter stick, all of that is going to not be fat. I can't use all that much fat, so I can have to store fat. There's no problem in storing fat. In fact, our blood is full of free fatty acids all the time. In addition, we have fat on us everywhere and we can store fat. And this is a different fat from the fat that we have created in that when we create triglycerides, we create 3 types of fatty acids chain linked together. In a certain proportion, there will be a certain amount of saturated fat forming a certain amount of polyunsaturated and certain amount of unsaturated fatty acids from that. And so when we're looking at what we can do, there's just a limit of what we can do in terms of triglycerides from the food, like omega-6, certain types, and omega-3. We can't make it all out of watermelon, but we can certainly saturate fat, and we can also make saturated fat out of glucose, and we can also make monounsaturated fats and certain kind of polyunsaturated, but not all. But if I eat butter, the fat in the butter, if I ate grass-fed butter, also contains omega-3. So it contains some omega-6s. These are fatty acids that are building blocks that we use and are not fuels. And so there's a difference between the kind of fat that we have when we eat versus when we make ourselves. And then, of course, I can eat a stick of butter with 2 bites. I actually like to eat, not necessarily butter, but I like to eat it. Whereas if you give me a whole watermelon, it's going to take me a whole day to eat that because it's just going to fill me up so much. But if you have given me a little bit of butter, I can eat that in 5 minutes and I'm set for the whole day and I can spend my energy elsewhere. So between the two, there's going to be a very big difference in how much energy my body has to put out to store that energy, how much energy it needs to use to convert that energy that I just ate into something that it can store. And so given that I ate the watermelon, it has very little nutrient value really in it. It's just the glucose, and glucose is just pure fuel. We as adults cannot make anything out of glucose other than fat or use it as glucose. We can't make protein out of glucose. We need some glucose to assist the protein generation. But in order to build our body, build our muscles, build our bones, to live, we can't just eat glucose. It just doesn't work that way. So then we come now to eating protein. So as I noted earlier, in order to get 1,000 calories out of, say, ground beef, you would need to eat approximately 400 gram, which is approximately 14 ounces. So, and if you eat, say, ribeye, you would have to eat about 16 ounces. The ground beef has more calories in it because there's more fat maybe in it. This database assumes that you remove all the fat from the ribeye. And so when you're looking at eating protein, a large part of protein is not going to be converted into energy. Protein is not our energy source. We can use some parts of it as energy once it's converted into glucose or fatty acids, but we use protein primarily as building our body. And I'm not just talking about muscles. We all have muscles, but that's not what I'm talking about. You have to consider What else is made of protein? My tongue is protein. My skin is protein. All my cells are mostly protein. All my brain cells, all my DNA, all of these are made of proteins. My Let's get back to muscles for a second. Muscles are not just the muscles that's on your skin. My tongue is a muscle. My heart is a muscle. My stomach is a muscle. All my blood vessels are muscles. And even my intestinal and colon, all my GI tract is muscle. And so we have a lot more muscles in us than what we understand to be muscles. So when we're talking about eating protein, it isn't just for building muscles, but it's building for muscle molecules or muscle cells all through our body. And also, 40% of our bones are made of protein. And so, when we're talking about protein, obviously you can see that there's a huge difference of how we can use glucose, fat, and protein. They're very, very different in what they do. So, we can't say that calorie is a calorie. So, if I eat 1,000 calories in watermelon, you can bet your life on it that I'm going to be using that very differently from if I have eaten 1,000 calories of meat or 1,000 calories of fat. It's going to be just very, very, very different. And so if I'm looking at CISO just from this perspective of all calories are equal, I can immediately see that that is totally false. Another thing I wanted to bring up with this one before I move on is carb loading, because so many people, you're probably familiar with it if you watch any of athletic programs or have an athlete friend or somebody who is running a marathon, even from within the migraine group who's just joined us recently. They all will be familiar with carb loading. And so carb loading would happen before an event. So say you're going to run a marathon tomorrow, then you're going to start carb loading today. So what they do is they load up on pasta, watermelon, anything possible in order to have enough energy the next day to run a marathon. And while this all sounds really normal, right? You need a lot of energy for tomorrow, so you're building up a lot of carb energy. The problem is that, as I mentioned earlier, glucose cannot stay in the form of glucose in our body. And we have great limitation for glucose storage in our kidneys and in our muscles. And all the rest of the glucose is going to have to turn into fat, triglycerides. And if I'm carb loading, by definition, I'm not in ketosis. So am I going to be able to use all those fats that I have just consumed? And clearly, this isn't going to be something that I can do. And so when we're looking at people who are preparing for a marathon and they're carb loading, I have often commented on that, is that what exactly are you doing? You're just really increasing your weight and you're increasing the effort on your body to be able to break all that down, and you won't be able to use the carbs as stored energy anyway. And so that's why you see people throughout running a marathon or whatever else they're doing, they loading up with gel because they keep on eating the gel packs because they know that they just simply don't have enough, right? So it's kind of silly to have to carb load. And so you can tell clearly just from this alone that there's a major problem with the idea of CISO because it just doesn't work that way. And then if you're in ketosis, while your body is going to quit using ketones the moment you ate some glucose, because it has to get rid of the glucose first, it's a priority to get rid of it, it actually isn't true that we are preferring the glucose. So if you look at textbooks, and we have many textbooks by now, and I also posted a link to a video by Dr. Saivas, who explains that about 85% of our body doesn't use glucose at all. Our heart doesn't use glucose. Every now and then it may use a little bit of glucose, but its primary fuel is actually fat. And if the heart switches to be a model for using glucose, then it starts to create lactic acid, which is a buildup of muscles. And because the heart can't stop like we can with our muscles, and we can stretch out and we can take magnesium and a hot bath to relax our muscle ache, which happens as a result of lactic acid buildup. The heart can't say, okay, I'm going to stop now a little bit to rest. It can't. If it does, you just had a heart attack. And so many people who have heart attacks may in fact have heart attack as a result of the heart switching to use glucose. It may not have access to using fatty acids. Why that is, it's beyond the scope of this discussion. But so you can see that um, there's the seesaw argument only works in mathematics because whatever energy you take in, you somehow have to expend it. The problem is that this somehow have to expend it isn't explained. It is assumed that you can just eat an apple and get the 100 calories from that and then go on the treadmill and run it off in 10, 15 minutes. But that's not the case because that glucose from the apple, particularly if you're not eating the apple while you're running, if you're eating the apple while you're running, you may actually be able to run that off. But if you're eating the apple before you ran or after you ran, it's going to be stored. So it's not going to be equivalent in terms of what calories you burn. And so there was a question that came up by Andrea Katz asking, well, let me talk about some of the exercises, Dan. That would be good. So this is a good question to bring up right here because if the seesaw doesn't work, then does the energy output from an exercise impact how much food you ate? And clearly, there's some connection, but very minimal. So let me explain this. So if I eat some food, like right now, I eat, and I immediately, while eating, I am exercising like crazy and I'm working it all off. And I'm eating the kind of fuel I can immediately burn. And I'm not going to name that now, what that is, because it depends on our uh, way of eating, right? Whether we're in ketosis or we are not. If we are looking at the exercise this way and we're using up the energy while we're eating, provided that we know exactly how much energy we just ate, and provided that we believe that all that energy is going to be converted into the kind of energy our muscles can use. And by muscles also include muscles that are not directly used, plus the bones, the heart, the lungs, every part when you exercise is working, correct? So when you're looking at it that way, you have to look to see, is that amount of food that you're eating, is it going to be all burnt by the exercise? Because if it is, then you couldn't possibly improve any part of you. So let me talk about this improvement. Every cell lives only for a certain length of time. Your blood cells live to be, I think, 10 days, the platelets live to be 10 days old. The blood cells live for about 3 months. Your skin cells live for about 3 months. Your bone cells live for about 15 years. Your neurons live to be forever, all through your life. You can add some changes, but basically they're the same ones. Your stomach and your intestinal cells replace every 2 days. And so when you're looking at all your cells that are replaced, well, if you just spent all the energy exercising that you just ate, what's going to happen to your cells? Is your skin going to peel off and not be replaced? Is your stomach lining going to just die and not be replaced? Are your bones going to just break up because you've used all the energy and they're not getting any replacement energy? Obviously not. So you can't actually look at energy that you ate and the exercise that you do as an equivalent or even connected statements. They're completely disconnected. In fact, it is very well understood that some exercises actually make you hungry, while others are completely blocking your hunger. So you can't even say that there is a clear connection. In fact, I had a conversation with Dr. Sipes about this, that if you do reactive, or not reactive, but resistance exercises, such as weightlifting, you can't eat after it. It's really fascinating. I used to do a lot of weightlifting, which I stopped now because of my shoulder. But I used to come home and I would not be able to eat for the life of me for about a good hour and a half after that. I would be full. It was just like an anorexic experience. And actually, he was calling it anorexia. This was a private email. It's not in the public. It causes an anorexic response. And that's because it works in a different way from when you, for example, go out and run. So these days I do a lot of hiking, and I can hike 3 to 5 miles every time I hike, and I come home starving after each time. But when I did the same amount of energy output in weightlifting, I was full and I couldn't eat. So, can we say that there's any connection between exercise and food in a direct manner that's easy to explain? And we can't. And so, the impact of the exercise and the type of exercise for weight loss is what? Is zero. I have to say zero. It has a zero impact. What has an impact is the type of exercise and of how much you eat, not on how much energy you expend. And it clearly has nothing to do with weight loss. Actually, you may gain weight. If you do weightlifting, you don't want to lose weight. You want to gain weight because you want to gain muscle. And that's weight. Muscles are heavier than fat. Whereas if you do endurance, you want to be reduce weight because it's heavier to carry a lot of weight on your body. And so if you do both, you actually undo one with the other. So you really should be doing one or the other as your primary exercise. If, for example, I do athletic or aerobic exercises and go out and do a run, a 2 mile run in the morning, and then I'm starving, and when I eat, and I eat whatever I need to, and then in the afternoon I do weightlifting, and then I can't eat whatsoever. Not only that, my eating is disturbed in both directions, but also if I weightlift, I become heavier. That puts me at a disadvantage in my running and in my endurance exercise. I should have much less weight. But if I'm running and doing endurance exercise and I'm dropping all my muscles, then I can't lift the weight. So you can see that there's no clear answer here. And we all need to exercise based on whatever feels right, whatever we prefer to do, what our body tells us to do. And then we have to eat according to how our body responds to our environment, which is independent from the exercise. And it's not independent from movement, but it's independent from exercise. So if you look back at tribes, in ancient tribes, or even the modern current living tribes, I put a link a few talks ago to an Amazon series, Amazon Prime, the film series, documentary series called Tribes, which is 4 distinct, separate little film segments, I think 40 minutes each, documentaries describing and visiting and living with 4 tribes and explaining how they live. And you can see that not one of them is ever exercising, but they are very active. So they have these dances and this singing and these ceremonies, and they're jumping up and down all day long for the fire, for the eating, for whatever occasion, greeting of the sun, greeting of their gods, whatever they're doing. They're physically very active, but they're not exercising. And of course, you also have to note, if you watch these 4 tribes, is that not one of them is consuming any carbohydrates other than milk. And so, but that's another story, and they want to get into that. So, what are the best types of exercises for migraineurs? There's no such as best, there's such as worse. And so I recommend not to do yoga, because yoga is definitely not very good for those of us with EDS, Ehlers-Danlos syndrome, where we are hyper flexible, and is also not very good for our cervicogenic area unless you are working with a trainer or you are a trainer and you know precisely how to prevent the ensuing problem from yoga. So I don't recommend yoga. I know many people are crazy about yoga, and many migraineurs are doing yoga, and I have no problem with it. But just know that because of our cervicogenic issues and because of the comorbidity of migraine with EDS, it seems like not the best of exercises. I would recommend, particularly for EDS, I would recommend weightlifting. Just use a proper position. Make sure you don't do what I did, which is hyperextending my elbow. If your joints are very weak, make sure you wrap under or above, not the joint itself. You don't want the joint to be protected. You want the muscles to build up. And so there are tricks by which a particular muscle can be built up stronger by blocking blood circulation to the muscle. So there are many ways you can study up on it. It is important that you strengthen your joints. strengthen your bones. So you need to have weight bearing exercise. Walking, running, these are all good weight bearing exercises. Jumping is good, but again, then you have to be careful with what you're doing. And weightlifting is excellent, but so many people get hurt because they're just following YouTubes, and oftentimes the YouTube is really not the way to do things. You really should talk to or have a trainer to do it the right way. And even that way, you can get hurt. So it's critical that you do things right. It's more important that you do them right than that you do them. So now let me get to the more recent questions that I have received. So Carol and Sweeney was asking several questions, and these are on cholesterol. So I thought this is an important discussion for us because so many people are concerned about cholesterol because there's just a huge push against increased LDL. And so we need to understand what LDL is. We need to understand what cholesterol is. And she's very specifically discussing I believe it is apolipoprotein A. And so let me talk a little bit about cholesterol. So if you look at under files in cholesterol, you're going to see what cholesterol is. So we have a document that describes how cholesterol is formed and what it is. And then we also know, of course, that cholesterol is not fat. So a lot of people confuse fat with cholesterol. In other words, if you eat fat, it doesn't mean it's going to increase your cholesterol because they're two completely different substances. Okay. So what Carol is asking is that in her family, there's a lineage that shows that a lot of people have high lipoprotein A, and they also Carol herself had 90% blockage in her carotid. Carotid is your artery coming and going from the brain, and so that can cause a stroke. And so she was concerned about increasing fat, and that she has to limit eating fat as a result of the carotid blockage. So let's discuss this. First of all, apolipoprotein is just a protein ball. It's an LDL protein ball, or a lipid ball, I should say. I'm sorry, it's an LDL lipid ball with a protein on top of it, which goes around and it just simply marks it. I'm an A type. And so there we have A and B type. And we have, of course, the fluffy ones, and we have the dense ones. And so lipoprotein itself is not cholesterol. Many people confuse LDL, for example. It's a low density lipoprotein, and HDL is a high density lipoprotein. But it's a lipoprotein ball. It isn't the actual cholesterol. It's a little ball in which there is also cholesterol, but there are other things. There will be all your fat soluble vitamins and minerals will be in this ball. So you're talking about vitamin A, E, D, E, K. All of these are going to be in this ball. So if they reduce your cholesterol because they say it's high, what are they reducing? They're reducing your fat soluble vitamins. Are you sure you want to do that? So let's talk about a little bit more about LDL and what the lipoprotein A is. So lipoprotein A is a type of LDL which is unhealthy or undesired. This is the one that our body is supposed to get rid of and dispose of. And if you have too much of it, then that can be a problem, because that can in fact cause a problem, particularly for people who have some issues with their arteries and so forth. So we have to look to see, number one, why do we have issues with the arteries? Why would it be a problem to have any kind of a cholesterol in us, given that we make it, it's so essential for us? What are they used for? And what can we do about if we have a condition that tells us that we should reduce cholesterol, such as, for example, I don't have the high cholesterol, but I do have the high triglyceride, which is an inherited condition. And so we can talk about that as well. So let's first of all understand what cholesterol is for our body. Our body, every single cell needs cholesterol. Every single brain cell needs a lot of cholesterol. The myelination, which is the white matter and it's around every single brain cell in order for the electricity to pass through, is made from, literally, fat and cholesterol. It's called the white matter. It takes up 85% of your brain. It is fat and cholesterol. So why on earth would you ever want to cut back on fat or cholesterol? That already is a problem. If you have a problem with deposition in your arteries, or carotid in this case, of cholesterol or any fatty substance that we call cholesterol or plaque, because it shouldn't stick there. It doesn't belong there. So why did it stick there in the first place? And so we need to look to see, would nature naturally cause obstacles in our blood vessels for cholesterol such that it may kill us later? And again, let's go back to tribes. And they do find that some tribal members have atherosclerosis, a little bit of plaques here and there, but not one of them has diabetes, high blood pressure, calcification. They're all of them, whoever they gave the calcium score to, they're over zero. So clearly, the fact that you have some cholesterol in your blood that may even be on the walls of your arteries isn't a problem. It seems to be completely natural. So what does it do and what does it mean? So when we're looking at cholesterol, we have to understand the role of cholesterol. So first of all, as I noted earlier, over 80% of our body actually uses fat. And so fat is an essential element more so than anything else. So if we reduce fat in our diet, what are we doing? We are hurting ourselves. Fat is not the problem, given that we even store glucose in the form of fat. We clearly need fat, right? That is our energy storage form. So reducing fat in your diet is the wrong thing to do. You need to look to see what caused your artery or carotid to have this deposit on the first place. And we know that arteries, and the carotid is an artery, have to become flexible, have to stay flexible all their lives. So as we grow from a fetus to an old adult, our blood vessels aren't expected to change. They may get a few wrinkles, just like our skin does, but they aren't expected to change in the way that you would see a change we see today. So why do we have problems with strokes and heart attacks? It's because of what we eat that we shouldn't be eating, which causes the modification of your arteries and your carotid. So if you had a 90% blockage in a carotid, it was because you have caused such an incredible inflammation that this inflammation itself has created the plaque. So how does this happen? This is very well explained by that video I referred to earlier by Dr. Sipes, but let me explain it a little bit here. Your blood vessels have several layers of tissues, and one of these tissue layer is a very thin layer that is very much on the inside of your blood vessels, which is coated with a glycocalyx. And if you've been paying attention to my COVID posts, then you know that this glycocalyx is on top of the endothelium. Endothelium is a layer of the cells, which cells are just tied together and provide a protection. It's like one layer of an army holding protection to make sure that nothing is going to cross that wall. And so this way, the blood flows in the blood vessel, and whatever is outside of the blood vessel stays outside, and there's no mix unless there's an intent to mix. So what happens is, if you eat foods that are inflammatory, and we know what these are, in addition to glucose, of course, we have grains, vegetable seed oils, all of the high starchy fruits and vegetables. These are all full of inflammatory matters. So what they actually do is the glucose that is in them and release, and the fat, in this case, in the vegetable oils and whatever, put that aside for a moment, and just looking at the carbohydrates themselves. A large load of carbohydrate in the blood literally kills off the glycocalyx. So glycocalyx is like very, very fine little hairs that are very slippery. It's like the fish in your hand. If you hold a fish in your hand, it will slip in one direction but not the other. And so the glycocalyx is that way. It's the little hairs which glide your blood to flow one way and prevents a block from flowing the other way. And so this helps your blood to flow in one direction to retain the circle. And of course, we know people who have problems with this, and that's called POTS. But also, when you eat a lot of carbohydrates, it kills off the glycocalyx. And so when the glycocalyx is gone, the endothelium, these little cells that were standing one by one, as I noted earlier, suddenly curl up because the glycocalyx is gone. They need to form a protection, but they can't, and so they curl up. So when you took something that was this big when it was flat, and then it curled up, it's going to become only that big. So what happened to the extra space in between them? Suddenly, they're not holding hands. There are spaces in between them. And as the blood is flowing, and the blood has particles in it, the blood has all kinds of things in it, including glucose, fat, cholesterol, vitamin E, all these kind of things are flowing in the blood, right? Salt, potassium, everything is flowing in the blood. Suddenly, we have these spaces between these cells. And so some of these elements, these are minerals that can deposit. These minerals will start depositing. And so when you have a deposit and there's a disagreement how it actually happens, there are considerations that the cholesterol, the LDL particles actually go inside the cells because they're found there, but it is unclear when they go inside. But you can see that when you have a cell that used to be this big and now it's only this big, the space around it is now freed up, and now everything will get stuck in there. You try that. You just create, lay out a piece of meat, for example, put little cuts in it now, and then spread it out with salt. You're going to see the salt is going to get stuck in the little crevices that you have created. And so this is where the problem lies. It's not that you're eating fat, but it's that you're eating the fat or the cholesterol or more carbohydrates when your arteries are already damaged. So you need to look to see what caused the damage. Can I prevent the damage from being caused? And of course, when you had the 90% blockage of your artery, the carotid artery, this was probably at the time when you were still eating a lot of carbohydrates. So now that you stop eating carbohydrates and you still have the blockage, but now there's no longer necessarily the method, the means by which anything can get stuck there. So the goal of our change of diet is to reduce the inflammation, to allow our endothelial cells to again grab each other and hold each other, and to provide a protective mechanism of the veins, so that nothing that is in the vein is going to, or arteries, is going to leak out into the cells, and nothing that is in the cells is going to leak into the blood. So there will be a lot safer passage of your food. There's not going to be any leaky gut. Leaky gut refers to the same phenomenon in the gut, but the gut itself is also lined with an endothelial cell, exactly the same way as the blood vessels are. And if you're eating inflammatory foods, they too will shrivel up and become inflamed. Space in between them is going to cause leakage. So there's no difference there. So the blockage of the artery isn't from the fat. It is what was eaten together with the fat and with other foods. And there's also some evidence to suggest that the LDL is really there to help as a glue, to glue down the damage so that there is not going to be a tear. Because when your endothelium is all swollen up and there's space around them, there's a potential that blood may go through. In fact, this is exactly what is happening in COVID, where blood, in fact, does go through as a result of the virus attacking right in between. And this causes then a host of conditions, including the release of all kinds of markers that cause clotting. And this clotting mechanism is the one that basically kills the people. The clotting can happen in the heart, in the brain, in the liver, in the kidney. It's just about anywhere you think of. And that is going to be the fatal it's the same process though. So the moment there's an inflammation there, and so how do we prevent an inflammation? It's by not eating anything that is inflammatory. So when we're talking about cholesterol very specifically, in terms of what you had and what you have in your family, including the lipoprotein A, it is only high as long as you have inflammation in your system. So if you stop having inflammation, there's no reason for cholesterol to become problematic. And that's because cholesterol is also part of our immune system. And so if your body is inflamed, the cholesterol is going to change roles as well. It's going to be a different kind of cholesterol. So some of the cholesterols are the small, dense cholesterol, which would be equivalent to the lipoprotein A. Those are damaged cholesterol particles. Those should be taken out of your body. And if they aren't, then there's a problem. There's inflammation in your body. That's not caused by cholesterol. Cholesterol is like a response to the inflammation, and having high lipoprotein A is a response to the inflammation. It is not the inflammatory factor. So now let's talk a little bit about the genetics of how this can happen, because there are definitely genetic conditions like ApoE4 is very well understood to be genetically associated with a higher uh, problem in terms of getting a heart attack or any kind of heart condition, and therefore higher cholesterol, etc. But all of these have to be understood in the context of insulin resistance. Let me explain that ApoE4, which is considered to be the most critical in terms of having high cholesterol, ApoE4 is the default human genotype. So we evolved as from apes and other hominids to what we are today with the ApoE4 gene. So if this was harmful, and at that time we lived on animals and scavenged, and we didn't eat carbohydrate, didn't even exist this much carbohydrate as we do now. But even if we ate carbohydrates, it would have been seasonally and just whatever we could find. Most of the food that we ate were insects, small animals, scavenged large animals, etc. So if we developed and evolved into who we are today on eating fat and eating meat, how could that possibly have been something that with an ApoE4 gene, which was at that time the only gene, we're still here? How come we didn't die off? I mean, what the modern hypothesis suggests is that if you have ApoE4 genes and if you eat meat and fat, you're going to die. Well, that just doesn't work that way. No, you will die faster if you have a high carbohydrate diet. Because if you look back in human history, we didn't have a high carbohydrate diet. We didn't eat carbohydrates. They didn't even exist. We could eat some barky stuff. The carrots even were inedible. A watermelon was this big, mostly seeds, and it had almost no glucose in it. There were some berries seasonally, minimal. So what carbs were we eating? We weren't eating any. We now evolved to eat grains and carbs. We didn't eat those before. And so we need to look to see and return to our old way of eating to some degree. I mean, we can't fully return because we have genetically been modified by now. So in terms of somebody asked, and that was Cheryl asked, and also Lacey Timer asked something else, but Cheryl Koch asked about familial hypercholesterolemia and hypertriglyceridemia. Because I have one of the two, and I guess her family has the other. And so it really is quite irrelevant because, again, context. So we need to look at in what context we have those. I have the genetics for having very high triglycerides and having the kind of conditions where I would get all kinds of cholesterol marks all over my face and my eyes and my body, huge cholesterol collections. This is the hypertriglyceridemia part of it. And the only thing that I have is really circle around my eyes. I don't know if you can see that. I have a circle around the eyeball on the inside. The retina is like a white circle. And so I have the white circle. I've always had it all my life. Nobody knew what it was, and now I know what it is. It is that I have this gene. And if I were eating a diet rich in carbohydrates and also would eat a lot of meat at the same time with high fatty meat, maybe I would come down with the kind of condition where I would end up having cholesterol patches everywhere, including the eyes, typical, the face. I don't have it anywhere. So it isn't really a problem. And also to have the hypercholesterolemia, it means that your LDL is over 500-600, it could go up to 3,000 and so forth. If you're a child and born with that, it's a genetic disorder, you may not survive till the age of 10. And in that case, it is definitely a problem. But if you have survived into adulthood and you're still here at age 30, 40, 50, 60, your chances of having any problem from it, 0, because you have managed your diet the proper way, or you now have a way to understand to manage your diet the proper way, and it just simply isn't going to happen to you. So genetics is a potential, it's an opportunity. It isn't a fact. You can have genes for, like I have the genes for leukemia, and I had family members who died in leukemia. I'm still here. Will I die from leukemia? Maybe. But for now, I don't have leukemia. So you have to look to see the switch on mechanism of the gene. Genes there are there, but it doesn't mean they're active. They need to be switched on. So here's, for example, the migraine genes. They're there. We are here learning how to switch them off. Okay, so I haven't had a migraine in ages, even though I have a migraine gene, right? So we learn how to switch them off. Lacey L.A. Timer is asking, is there a relationship between hypothyroidism and LDL cholesterol? And not to my knowledge whatsoever. In fact, a hypothyroidism, unless it's Hashimoto's, is simply not enough iodine. So if you don't have Hashimoto's, but you have hypothyroidism, get some supplemental iodine and start piling them on. We have instructions under the files for that. It's a very simple thing to completely prevent, absolutely independent from LDL cholesterol. Now then, Chrissy Dasher, is there a caution or concern for women fasting if they're over 40? Answer, absolutely not. In fact, the more the better, because over 40 is when we tend to start depositing most of our fats in the wrong places. This is the time to prevent that. So if you haven't gotten any fat yet in the wrong places, this is a very good time to prevent that by activating your body organism for not storing, but using the stuff instead of storing it. And you can store a little bit, but not much. But there's absolutely no reason why fasting would be to your disadvantage, unless you're very thin. If you're very thin, you don't want to fast. And what are the macros for losing weight? Well, that's a great question. I have no idea. It seems that it's independent from the macros. And that's because weight, as I've discussed CISA already, has nothing to do with what we eat or how much we exercise. And what exactly weight has to do with is more to do with our hormones. And I don't mean sex hormones, so I don't mean the estrogen and progesterone. I mean insulin, leptin, ghrelin. You got a host of hormones that are responsible for weight gain or weight loss, which are completely out of your control. Can you control them in any way? You can try. Fasting is a good way. If you stop eating, you're clearly eventually going to lose weight. The question is, what else is going to go wrong? So we don't know. All I can say is that no matter what macros I have ever consumed, and no matter how much I have eaten or not eaten, I'm famous for gaining weight on a day of fasting. I'm not kidding, seriously. So it really is pure hormones. And I have tested, for example, my leptin. I recommend that everybody test your leptin. It's on the list for us on the blood test. And leptin is a hormone inside the fat tissue. And what is interesting about leptin is that the more you have, the fatter you're going to get. That's just the way it works. And my husband and I, we both went to get our leptin test, and he is thin as can be, and he eats 5 times as much as I do. And he's eating all day long, basically. He's eating keto, but he's eating all day long. He's eating 5-6 times a day. And at each meal, he's eating much more than I do. And he even snacks. This is snacking with cheese and meat, but it's still snacking, right? And he is thin as a pencil and is trying to gain weight. Excuse me. And here I am eating only once or twice a day. I've tried once, it's not working, but twice a day is what I'm usually doing. And, or of course, I don't eat at all because I may fast 1 or 2 days in a shot, and I'm eating much less than he does. And I'm only eating twice a day, but much less than he does. And I'm active. I go hiking, and I used to weightlift, which I'm not doing now because of my arm, but I'm still hiking 3 to 5 miles a day. And I'm gaining weight. What can I do? I'm gaining weight. And so our leptins compared. His leptin, I'm just going to give you exact numbers, is different from female, but I just give you the numbers. And once you get your test, you're going to understand the differences. His leptin is 4, and mine is 44, okay? Women are supposed to have higher leptin because we have more fat, but it should be maybe 4 times that much, not necessarily 10 times that much. And so yet I'm eating less, exercising as much or more, and And no idea what would make me lose weight. No, if you figure it out, let me know because I have no idea. I've tried everything. Exercise will definitely not make you lose weight. Um, then Kelly Lisa is asking, I've always been interested in knowing some background on how you first approached your investigations in migraine cause. Like what was the starting point that led you to the process of discovering electrolyte imbalances as the cause? And do you think it could have been done had you not been a migrainer yourself? It's a great question. Let me answer the second one first. I don't think it could have been done if I were not a migrainer because I would not have been able to understand the connection between salt so clearly because I would not have been able to experience it. So the key part of the discovery was, I think, that I could try stuff on me. I could experiment and I could say, wow, this worked. And then I could repeat and say, wow, it worked again. Why did it work? What did I do? And sort of isolate what may have worked. And so the background really my investigation was this, is that I first didn't read anything. I just wanted to see what would work. And everybody was talking about magnesium, B2, all these things. And I added all these things, and not only they didn't work, but they actually made things worse. And it was after I decided to read every single article, every single book, and I decided to also read up, pull my old biology textbooks, and I said, okay, what exactly is possible here? And then I've noted it in the book as well, is that it opened randomly at a page, which was a cell. It was a cartoon drawing of a cell. And it just hit me at that time that, whoa, I never ever considered things at the cellular base. I always looked at the body as the body. So when you eat some food, you think you're eating food. When you're drinking, you think you're eating something, drinking whatever you're drinking. But it isn't true. I mean, even the smallest of tasks, say, you take a deep breath, it's not your body that is taking your deep breath. It's a particular organ that passes the oxygen from cell to cell. So everything that is happening in our body is from cell to cell. It's at the cellular level. And within the cell, it is down into a molecular and atomic level. It's down to the electron. And it is something I'm now quoting in my book, that is the second edition, or third edition that's going to come out, that says that basically life is about an electron finding a place. An electron is a negative charge. If that electron finds a place somewhere and can connect to a positive charge and neutralize, that's it. That became the end. And so everything that we eat, everything we drink, everything we do is based on these electron exchanges. It is the negative to positive side. Everything we do is electricity. Everything. And so in the new book, I'm going to be making it clearer of how this works and why this works. But in order for me to understand migraine and the salt connection, which was the number one that I understood, I needed to understand that I have to work at the level of the cell, and I have to work at the level of the electrons within the cell and within the food. Laura Harding Graback asks, how far into your research did you make the discovery of the link between insulin, electrolyte balance, and eating meat fast versus grain fruits, etc.? Very late in my discovery. So we already had the group, actually. The group started in 2014 when I wrote the book. And it was at about that time that I started to realize that some carbohydrates may not be good. In the first book, those of you who read the first book in 2014, which was a green, very thin book, which was just my experience, I still recommended people go to a McDonald's burger with bread and French fries and everything to eat that if they have a migraine, because it had a lot of salt and it had a lot of potassium. And so I recommended to eat that. I didn't recommend a Coke anymore, but I still recommended the bread. I didn't yet understand the importance. So it didn't happen up until maybe, I would say 5 years ago. So 2016 or so. By the time I was working on my second book, I understood. So 2015 is when I started to understand the connection of carbohydrates. We still have some posts from 2015 when we're experimenting with all kinds of different fibers and different kind of foods. We still had sweet potato and potato still was on the menu, and we still ate different kind of things which we no longer do. So I would say 5, 6 years ago is when it really hit me that there's a carbohydrate connection, and that happened because I discovered this book. Longo's et al. Wrote a book about. It's called the Harrison's Manual of Medicine. 18th edition is what I have, and I bought this. Total of them just looking it up. It's over 1,000 pages, but on page 4, it explains the role of glucose in removing salt of sodium and water from the cell. And that was basically the light bulb moment when I read that book. And it's yet just one tiny sentence that no doctor ever remembers for. That was the most important sentence in understanding migraine in my mind. Let's see, Amy Baker Stout. These are some of the later questions that I got today, so I haven't had too much time to work on them. But she's asking, she's transitioning from CD to keto. What does this process or pace look like? So when you CD, you're only eating animal products, and you can of course eat mushrooms and kelp. So these are not carbohydrates, and they're not plant products, not plant-based. But when you're on a carnivore diet, it doesn't mean you're carb-free. It just means you're plant-free. So you can have carbohydrates. So milk, for example, is a carbohydrate. Cheeses have carbohydrates. Oysters, my favorite food, scallops, mussels, all of these have carbohydrates. In fact, the other day I was looking at, sent a panic message to Christine. I said, wow, Christine, look, they now in Chronometer added carbohydrates to meat. I added my ribeye steak that I put in, and it was a huge ribeye steak, and it came up with like 4 carb grams. I said, wow, I don't think I've noticed before that my steak was listed in Chronometer having carbohydrates. And of course, we know that muscle meat has glucose in it. It's a glycogen, right? We talked about it earlier. So muscle has glycogen in it. It just didn't dawn on me that I'm eating a steak, and with that, I'm eating carbohydrates. At least I've never noticed it before. It may have been there, but because I always enter my food and I eat carbohydrates because I'm on the keto diet, it just never hit me in the eye that, wow, my steak also has carbohydrates. So you eat carbs all the time. So when you move from CD, carnivore diet, to the ketogenic diet, you really aren't changing that much. The only thing that, in terms of carbohydrates, the only thing that is changing is now you're going to be adding plant matter. And plant matters come with fiber. So the caution is not because of carbohydrates in general, but primarily because of the fiber. It's going to make you run, or it may constipate you, one of the two. But also because carbohydrates are instant glucose, whereas a muscle has glucose. And of course, if you eat liver or other kind of mollusks, you will get a bunch of glucose in you. The process by which they convert into glucose in your body is a little bit different from eating a teaspoon of sugar, as noted earlier with watermelon versus the steak and the fat. And so your insulin is not set to handle a quick release glucose, because when you eat carbohydrates in the meat, it's not a quick release. Your meat has to be digested. The glycogen has to be pulled out of it. It takes time. It's not like you ate sugar. You ate some glycogen in the meat, and so it isn't available immediately right away. But when you eat carbohydrates, it's a sugar in your mouth. It's sugar before it hits you. So your insulin will release a lot greater amount of insulin will release. And so as a result, you may end up with a sugar crash. So this is the problem when you transition. So we ask you to transition in terms of adding carbohydrates as plants because of the fiber and because of the amount of insulin that suddenly may kick in, and that it may cause sugar crash or reactive hypoglycemia, which we don't want. And so we recommend that you move to hypercarnivore first, in which you add just 1 or 2 carb grams from plants a day. Of course, if you drank milk, whatever, that doesn't count. You just continue. But we're talking about carb grams added from actual plant matter. And we want you to do that in order to reestablish your gut flora. And so the question is, how long should you spend in the hypercarnivore? Well, it depends on how your body reacts to adding back fiber. If you have no problems, no issues whatsoever, and you don't see any reactive hypoglycemia or sugar crash, then continue to increase, but slowly increase the carbs. because changes may happen later and you don't want to get into trouble. Then she's asking, she sees different types of keto in the guys, which is her goal. We don't know. It will go by trial and error. Keto is a lot more forgiving than protocol. So, like, I don't even necessarily follow the macros on some days. Some days I'm eating keto, some days I'm eating protocol, some days I'm eating carnivore. It's a moody kind of a thing. So once you're that experienced and you can prevent all your migraines, it no longer matters. It matters only on the protocol when you're still learning how to control your migraines and how to heal your metabolic syndrome. If you no longer have any of those, you do whatever you wish, just don't eat sugar, because then you're going to get your both of them back. So there's a limitation, but your macros won't matter that much anymore. And so there's no specific macros other than there's a guideline of how you start in keto, just like there is in the low carb high fat and also in carnivore. But once you're more advanced, you no longer need to, excuse me, you no longer need to religiously stick to that particular ratio. Then there's from Lacey at a timer. Then there's a link to a video from Insulin IQ in the guides about salt and insulin resistance. Like you said, you had a few things to add to. In the video, they discuss a study with a very small sample size being a good thing because it still shows an effect. However, small sample sizes decrease power and validity in studies. I'm not questioning the content, but how do you determine who, what to listen to with all of these new age nutrition experts? So excellent, two questions. So the first one, I don't really know which video that is, and because this was asked today, I didn't have a chance to look at it. But probably I discussed it in terms of the sodium, because we know that we have several different glucose transport channels and receptors in our body, but only one of those uses insulin. All the others use sodium, passive diffusion. And so when we're looking at insulin resistance, if somebody is eating a reduced sodium diet, which is the standard American diet is supposed to be a reduced sodium diet, and the USDA recommends to reduce the salt level to a very low level, then it's going to cause trouble in terms of taking glucose out of the blood. And there are studies that suggest a strong correlation. I don't know if there's a causal evaluation properly, now I don't remember suddenly, but that show that type 2 diabetes and insulin resistance are strongly correlated with a reduced sodium diet. So if the American or guidelines, the USDA recommends that we should be eating, I think it's 2,300 milligrams sodium a day. So it's a little bit less than a teaspoon. It used to be 2,400, now it's 2,300 milligrams sodium a day, which is one teaspoon. Then if I'm looking at some of the studies that have been released, one from the Lancet and another one, two from the Lancet and one from the British Medical Journal, they all will show that in fact the minimum sodium that a healthy human needs is upwards of 6,000 milligrams sodium a day. And they recommended that even those with a heart problem go to 4,500 milligram, and lower than 1,800 milligram, I think 1,500 milligram sodium, there's an exponential increase in all-cause mortality as a result of not enough sodium. So maybe this was the connection that you were referring to. In terms of the size of the studies and who to listen to, unfortunately, we can't experiment a lot with a lot of people for a long time. Financial reasons, also people change. Like, for example, if I were to run an experiment with migraineurs, I would literally have to lock all of you up in a room somewhere or in a hotel and block all outside connections to have a proper clinical trial. You'd have to slowly, after so many months, come off all your medications, get on the protocol, and then from protocol to get onto carnivore or to keto. You can see that it's very difficult to do that. It's impossible to do that with humans. So you can choose a short time period and you can choose a few people. And I'm not saying that this is 100% valid, also because people differ. And so what worked for me may not work for them. But it gives us a good guideline of what may happen. Now, in terms of determining the good science from the bad science, this is more important to discuss. So even with small people number, you can have very good science. And even with very large people number, you can have very bad science. So we have a lot of bad science out there because they're easier to do. So for example, if I were to give you a questionnaire listing all the foods that you could eat, and you had to choose what you ate in 2015 and 2016, how many bananas did you eat a day in 2015 and 2016? How many cups of water did you drink in 2015 or 2016 a day? How many cups of broccoli did you eat? How many cups of ground beef did you eat? Mind you, cups, right? These are the kind of questions that you're getting on the survey questions for the food surveys. And then they're taking this data and they're coming up with some numbers. But is it reliable, even though it may be containing 200,000 people? It's not reliable. I have no clue what I ate in 2015. I can tell you I still ate grain, but I have no idea what I ate. I don't even know if I ate banana. I have no idea what I ate. So I will make up a story. I can tell you what I ate without chronometer or any kind of a record keeping regularly. I can't tell you what I ate even yesterday. How could I tell you? How can I tell you precisely what I ate? And if I know that if I'm overweight, I'm going to underestimate what I ate. I'm going to deliberately say, no, I didn't eat any sugar or cake. And if I'm smoking, I'm going to say, well, I'm only smoking 2 cigarettes a day, or maybe now I'm not smoking. Or if I have some kind of a health condition, no, I don't have. So these are not realistic when the surveys are taken. Yet most of the studies that are large in number and that advise what we should be eating are based on these kind of studies. So these kind of studies are quite trashy. Okay? The real studies are the clinical trials, and we have a couple of them. And these clinical trials, there's one very famous one, and I don't remember the name because I couldn't prepare in advance, that was created by one of our vegan friends up in San Francisco, who showed, for example, that the vegan diet was better in terms of cholesterol and health, blah, 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 than the standard diet. But what did he do? In addition to putting people in the vegan diet, and then, of course, the control was the standard American diet, in the vegan diet, he also removed all of them from cigarette. He also consulted them on exercise and health, sleep behavior, made sure they drank enough water, etc. So what worked? Was it that they quit the cigarette, or was it the vegan diet? We have no idea. So even that study is faulty. So we had several studies of late where they actually compared, not of late, but since about the 70s or so, where they have compared, for example, fats, the saturated fat arm versus the monounsaturated fat arm or the polyunsaturated fat arm, which are great studies, but they only controlled for the fat. So the fact that one group may have eaten more sugar than the other, they didn't control for that. So I've just explained earlier that sugar and starches have and very high sweet fruit juices and alcohol, these all affect, and cigarette all affect how you respond to certain things. So whether they improved or not improved from saturated versus monounsaturated or polyunsaturated fatty acids, we can't really tell because we don't know how much they were similar in what they ate and drank in their other foods because nobody looked at them. So we can't really look. There are a couple of very recent trials that more or less look at the right things. There's one that I think just finished, which was done by Sarah Hellberg and team by Verta Health, which was looking at the application of the very low carbohydrate diet to people with type 2 diabetes. And I believe that that study is the only study that I can recall that is really sufficient in terms of the people they were the doctors were watching what the people ate, the medications reduced, how much sugar, the blood sugar. They all have the continuous glucose monitor, and the data goes to the doctor, and they're all checking their ketones, and the data goes to the doctor. So you really need to cover the whole thing in order to understand it. And the last thing is that most of the studies in the past looked at whether a particular diet reduced LDL or not, and they considered the reduction of LDL to be the benefit. So that was the goal to be reached. But nobody actually looked to see if the reduced LDL benefited the person's life in general. And now we know it doesn't. Actually, we have studies that show, 2015 studies in the annals, show that actually higher LDL is more beneficial in terms of life. And so all of these studies were set up wrong. So we can't really go by that. What you can go by is experiment it for yourself. If you feel good, if your personal health conditions are disappearing as a result of what you eat, then there is a great chance that you're doing the right thing and you're eating the right food. Um, there's a few more questions here. So, do I plan to do clinical trials? Not really, because of the complications I have just explained associated with keeping the people completely isolated, removing them from medication in a controlled manner. Some take 2 weeks, some take 2 years. There's just no way to control how long a person is going to take to reduce the medication. And then also, of course, the food has to be controlled. They can't go outside. I just don't see it feasible. Not to mention, it will never be approved by an ethical board until they consider high sodium to be a problem because we eat high sodium. So I will probably not run any clinical trials. I think that we don't need to. We know that it works, and that's all that matters. And people tell me, but it must be placebo. I said, well, if it's a placebo and you're able to come off of all your medications, your health returns, and you have no migraines, placebo, great, let it come. Okay, so another question is that since the protocol, the migraines removed from sharp pain to a dull ache, is it still migraine? That is still a migraine. It's just that it's now your brain is healing, and it takes time for the brain to heal. And you may not catch all the prodromes. And there's also a question here that you seem to be going from prodrome to prodrome. And in fact, you do, because now you know what your prodromes are, whereas before you didn't consider them and you just went into migraine. So now you can see how often your body is out of balance. So a prodrome is an amazingly good tool for you to prevent your migraines. You don't want to get rid of your prodromes, you want them. And your prodromes will reduce over time as you heal. And then you will find, like, I rarely have any problems. I still have one eye smaller than the other, maybe even I can, yeah, I can see it a little bit. And so that's the sign that I will take a salt pill. For me, that always means the salt pill, and then I will be completely fine. And the last question is, what is the status of your new book? Well, that's interesting because we have so much work and so many new people joining the group. I have very little time to work on it. So approximately, I would say 1/3 done. And the new book is going to be an updated edition of what we have now. And I'm about 1/3 corrected. It's going to be quite a bit of change. It's going to incorporate most of our up-to-date processes and also a lot more. And then I will probably write an additional book which will explain ketogenesis such that people could really understand what it is, what it is not, how ketones work, and what we're looking at. So I would expect, I'm hoping that by the end of this year, we will have the third edition of my book out, the complete guide. And then the year after that, the next book. So I have another questions. I think I answered all of them, and I hope you all have a great weekend. Bye. See you in the group.